Hey y'all, this is Mr. Heier. We're going to talk about conservation of energy today. Take a few notes. This is the last of our energy unit for our test on Friday. Um, Tomorrow, Wednesday, we're going to spend some time in class working through a couple more of these problems to make sure that you can do them. But take the notes today and try the problems that I give you, and we'll look at some more tomorrow, and you can ask questions tomorrow. All right, so the first thing in our notes is mechanical energy. The mechanical energy is simply the sum of the kinetic and potential energies. So E, which is mechanical energy, is Ke plus Pe. And we know how to calculate both kinetic energy and potential energy. Well, kinetic energy, of course, is 1/2 mv squared, and potential energy is mgh. All right, so now conservation of energy. This is the kind of why we've been learning everything that we've been learning. All right, so if I have this cart running down the hill, as it goes down the hill, right now it is a certain height above the ground, right? So it's got a full amount of potential energy and no kinetic energy if it starts from rest. As it starts to move, it goes downward, so the potential energy is going to drop, but the kinetic energy is going to go up. But the total amount of energy, the Ke plus Pe, is always going to remain the same. Okay, so this idea of a roller coaster, right? Roller coaster, what happens when you start, the motor, if you like, right here, kind of lifts you all the way up to the top, right? And the outside forces do work, and then this potential energy all of a sudden turns into kinetic as it falls all the way down. Right? So conservation of energy basically says the energy cannot be created or destroyed, right? It just transforms into different forms, into different types. So the total energy, mechanical energy, is Pe plus Ke. And so as one goes up, the other goes down, or when as one goes down, the other goes up. And sometimes they get transferred to other types of forms like heat and sound and light and things like that. So here in the example, again, the roller coaster starts up here with a lot of potential energy, right? And the kinetic energy here might be 0. And then it comes down here and it's got a lot of kinetic energy down here and not as much potential. And as it goes around the loop, it loses kinetic. It goes slower, but it gains potential energy, and then it speeds back up again. And it goes on forever and ever and ever. Now, if there's no friction or anything, it'll just keep going on forever and ever and ever. But we know in real life, there's a lot of friction, air resistance, noise, and such, and all those cause losses. And so the potential energy at the top doesn't always equal the kinetic energy at the bottom. There are some losses, and we'll look at some examples of that in a minute. Okay, here's a pendulum. Kind of the same idea. Right, the pendulum swings down. It's going to come all the way. It's going to come all the way down here, and so it's got a lot of potential energy here, and that potential energy turns into kinetic energy down here, and then it comes back over to here, and it loses that kinetic energy and turns back into potential. Okay, so in reality, does the roller coaster's final kinetic energy equal the initial potential energy? No, because there are losses. Energy is lost to friction, air resistance, heat, sound, all sorts of things. And the energy is lost but not destroyed, right? Just transforms into different forms that we can't use. So your total energy is potential plus kinetic plus anything that was lost in different forms like heat and such that we cannot recover. All right, so we're just going to work through a few examples here. Assume for this one, we're going to assume no loss of energy. We'll assume no loss of energy. All right, so the tallest wooden roller coaster has a height of 60 meters. If one of the trains has a mass of 1,230 kilograms when loaded, how much potential energy does it have at the top of the ride? So we know potential energy is equal to m times g times h. So 1230 times 9.8 times 60. 30.8 times 60. Calculate that with me. 723,240 joules. We're going to use that again later, so I might have to come back and look at that. Next part. What would the kinetic energy be at the bottom right? If there are no losses, then the kinetic energy at the bottom should equal the potential energy at the top, which is 723,240 joules. And what would be the speed? We know kinetic energy equals 1/2 mv squared. So 723,240 equals 1/2 the mass, which is 1230, times velocity squared. So that becomes 723,240 equals 615 v squared. We divide both sides by 615, 72,240 divided by 615. So we get v squared is equal to 1176. And so we take the square root of both sides. And the square root of that is 34.3 meters per second. Right now, will a real roller coaster go that fast at the bottom? No, because it's going to lose. It's probably going to be closer to 25 to 30 meters per second instead of 34 because it loses energy. Right. So now, if there is an energy, there is a loss. Says if the friction on the track loses or causes 60,000 joules of energy to be lost, what is the kinetic energy at the bottom? Okay, well, kinetic energy at the bottom would be 723,240 minus 60,000. 72,240 minus 60,000. That becomes 663,240 joules. Right, so that's the kinetic energy. Right, I'm going to write it up here. The kinetic energy is going to be equal to the potential energy minus the work lost, or the energy lost. Right, and that's going to be the work done by friction and all those things. So 663,240 equals 1/2 the mass times velocity squared, and I'll go through the same thing, and I'll let you all do the math on your own. 230, take the square root. It's going to be 32.8 meters per second. Right, so if we lost 60,000 joules of energy, going a little bit slower. Right, and that would be the new speed at the bottom of the hill. Sorry, I jumped ahead a little bit there. So what we did here would answer my question here. So the V would be 32.8 meters per second. I jumped a little bit ahead there, sorry. All right, let's try another one. 60 kilogram skier skis from rest down to the bottom of a 1,200 meter tall mountain. If there's no energy loss, how fast is he going at the bottom? All right, so he's going down a hill. Right, this is 1,200 meters. Right, he starts here, he ends down here. Right, if there's no energy loss, that means the PE at the top equals the KE at the bottom. Right, so MGH top equals 1/2 mv squared at the bottom. Right, so 60 times 9.8 times 1,200 equals 1/2 times 60 times v squared. 1.8 times 1,200 is, sorry, my light just came off. Let's see if I can get it to come back on. There we go, sorry. So that becomes 705,600. Notice the number, some of the numbers get really big here, equals 30 times v squared. So divide both sides by 30. Get v squared is equal to 23,520. And I take the square root of both sides. And he's going 153.6 0.4 meters per second. That's probably not the most reasonable answer. That's without air resistance and everything else, and friction and such. So he wouldn't be going near that fast. That would be incredibly fast. It'd be fun, but it'd be much more fast than what's possible. All right, so let's try one more. Child jumps off a tall rock into a lake. He enters the lake moving at 14 meters per second. How tall is the rock? So again, we do the same thing. Potential energy at the top equals the kinetic energy at the bottom. mgh at the top equals 1/2 at the bottom. Right? And notice I didn't give you a mass this time. Well, there's a mass in every term, so the mass actually cancels out. So you don't need to know the mass. All right, so it's really g times h at the top equals 1/2 v squared at the bottom. So 9.8 times h, because we don't know what h is, equals 1/2 times, what's the speed? 14 squared. Right, so 9.8 h is equal to 14 squared divided by 2 is 98. I divide both sides by 9.8, and it looks like I'm going to get h is equal to 10 meters. So it's 10 meters tall. All right, let's look at one more. This one involves energy loss. All right, the ones we've done, the last couple we've done have not dealt with energy loss. Let's look at this one with some energy loss here. All right, so 4-kilogram rock falls from a height of 1,000 meters, hits the ground moving at 100 meters per second. So what's the potential energy does it start with? PE equals mgh, 4 times 9.8 times 100. That's 3,920 joules. How much kinetic energy did it finish with? Well, kinetic energy is 1/2 mv squared. We can't assume that it's going to be the same now because we're saying there's going to be a loss. And we're given a speed here. So it's going to be 1/2 4 times 100 squared, which is 1/2 times 4 times 100 squared. And I get 20,000 joules. All right, let me back up real fast. I put 100 here. This should be 1,000, right? So this should be another 0 here. Right, so this should be 39,200 joules and 20,000 joules. Sorry about that. All right, so how much work is done by the air resistance? Right, well, the work done by the air resistance, the work done by the air, is just going to be the difference between those two values. Right, it's going to be the final 20,000 minus the initial 39,200, and we get negative 19,200 joules. The negative sign here means that it's losing energy. Right. And then if it took 20 seconds to fall, how much power did the air exert? So power is work over time. So we're just going to take the positive of this, 19,200 divided by 20. And that's 960 watts. All right, so the last one was just review back for what we did earlier when we did work and power. All right, so basically, I think it was the last one, yeah. So basically what we do when we solve these problems, right, you look at the potential energy at the top, kinetic energy at the bottom. If there are no losses, you set them equal to one another. If they're not equal, then typically the difference between them is the work done by friction or air resistance or whatever happens to be in the way. All right, so practice the problems that are given in E-class. We're going to go over a couple of them in class tomorrow. Get ready to ask questions if something doesn't make sense. And from here, we're just going to finish up and we'll start reviewing tomorrow and Thursday, and then we'll take our test on Friday. All right.